Hi everyone and welcome to AI Unboxed. In this webinar series, we go behind the curtain to explore what's really happening inside AI data centers, networks, and infrastructure. AI demand is accelerating at an unprecedented pace. Nearly 90% of operators plan to expand or maintain their AI infrastructure investments. Yet, many are already hitting their limits when it comes to scaling networks and compute for next-generation workloads. That tension between rapid growth and real-world constraints is exactly what we'll explore today. We are joined by leaders from Keysight to share their perspective on where AI infrastructure is headed and what it will take to support what's coming next. We want today's session to be interactive, so feel free to drop your questions in the Q&A panel as we go. Our experts are monitoring the chat in real time, and we'll get to as many questions as possible. With that, let's get started. To kick things off, we'll dive into key trends in AI infrastructure for 2026 and beyond. Take it away, Mike.
When you sit at the crossroads of network equipment manufacturing, high-speed digital design, and network performance optimization, you tend to develop a unique perspective on what the future might look like for AI data centers. In this joint keynote, Keysight's Joachim Peerlings and Ram Perry-Kruppen explore some of the key trends and technologies that are shaping the next generation of AI-centric innovation.
This picture, I showed this picture 6 years ago. We had an event here as well, and at that time, my son asked me what I do for a living. And I said, I enable 5G. And, he found that pretty cool, and he got 5G. I'm not sure if he does a lot with it. And this is my son today, 6 years later. And, and he asked me what I'm working on, and I said, I enable AI, and that really made him excited.
Hey, can you pour me some coffee? Oh, you have got to be kidding me.
I think there's a lot of work to do, and I want to talk about AI from the perspective of interconnect reach, all the way from millimeter and chiplet connections to chip-to-chip, scale-up, scale-out, and then DCI or scale-across and subsea, and have a couple of examples, how we collaborate with customers and also where we see the industry in terms of interconnect readiness. This is a collaboration we have with AlphaWave. They're really trying to get interoperability for chiplets. And what we do for them is that we, on the one hand, test transmitter in a test mode. And that gives us, it's a different channel, but gives us some idea on how the transmitter is performing. And for interoperability, you need to separate out transmit and receive. Then we test the receive side with a built-in self-test, and we build a behavioral model from those different receivers that we test. And then we test the direct link die to die from TX to RX. We de-embed that channel by physically measuring it with a network analyzer, de-embedding it. And then because we have this behavioral model of the RX, we can decompose the transmit and the receive, and that gives us a good understanding on how the individual transmit and receive portion work. And I think that's good progress. So this is electrical chiplet. If we look at optical chiplets, this is a slide from NTT Innovative Devices from Tomisawa-san. They have a 64 gigabit per second optical chiplet that they co-package with GPUs. They have a special membrane technology. You see that on the left-hand side that they integrate into their optical chiplets. And I think it's a good way to minimizing copper routes by having electrical chiplets and co-packing that with optics. And they plan to release this in 2028. When we go from chiplets to chip-to-chip connections, we had a PR with AMD, where we enabled AMD to show compliance for PCI 6. If any of your teams need pre-released software from Keysight, especially for compliance, let us know. It's always good for us to get hands-on devices so that when we release software, it's more stable, and then you can save some work in automation. So then PCI 7, it's chip-to-chip, but also interesting for scale-up networks. It's an alternative for UA-Link, for the Ethernet PHY, for UA-Link to use PCI 7. This is a demonstration that we did at DesignCon with Marvell. We had the 28 giga transfers over a 40 dB channel. I think those were good results. Then this is a slide from Candu, from Amin Chokolahi. He is the founder and the CTO of Candu. And many of you may remember the ZNSE5 effort from Candu that they did way back. So now they progressed this to build chip-to-chip and scale-up connections at 448 gigabit with only 66 to 77 gigabaud. So it's a copper MIMO link, a special coding. And how we help them is we build that coding into our equipment, and that way they can do an independent characterization of their transmit and their receive. Because the challenge with these codings is, if you just run back to back, you may do the same coding error twice and still get a good result. And then next year, when those chips come out, we will be able to show that transmit and receive work at 448 gig with only around 66 gigabaud. Then if we go to scale out, there's a lot of progress with linear pluggable optics. We hosted a couple of events here in this building in Santa Clara. And the next, if you're interested, the next Plugfest is probably around February. We haven't announced it, but we will have another Plugfest. And this is always a good way for us to get hands on devices and help the industry to work on interoperability. Then when we talk about linear devices, also co-packaged optics is, I think more projects on co-packaged optics since NVIDIA announced their co-packaged optics switch. This is also a slide that Tomisawa-san provided for this event here. And they do 6.4 terabit pluggable co-packaged optics modules. And you see, in the middle is the engine. It's a Tomahawk 6 switching silicon surrounded by those 6.4 terabit optical engines, and it's 32 times 200 gig per lane. And the idea is that this is field replaceable. So you still need to, unmount the heatsink if you want to exchange the module, but you see that the co-packaged optical module is pluggable, and that's a step further towards field replaceability and serviceability for co-packaged optics technology. Then multimode has come a long way. I think it's interesting if we look at 10 gig, 20 gig, how that progressed. And every generation, the industry was asking, is multimode, getting to a next generation. And we built a couple of prototypes that we gave to some key players in the industry. This is a slide from Broadcom that they gave me for today, and I think they showed good progress. But we also saw Radek over there. We had units to Coherent, Optolink, Semtech. I think there is an ecosystem that is ready to do 200 gig per lane multimode technology. And for those VCSELs here is with the same DSP, it's around 3 to 5 watt power savings if you look at an SR8 versus a DR8 or 2 times FR4. So I think good progress on the multimode front as well. Then if we look at 400 gig per lane scale out, we did a couple of demonstrations. This one was at OFC together with Lumentum. We demonstrated the indium phosphide EML at 400 gig per lane. We also helped, Sienna did a trial over 2 kilometers with McGill University and Hyperlight that we supported. Then also TerraHop had a demonstration at OFC. And also Marvell, they had the world's first electrical to optical link at 400 gigabit per second, and that also was demonstrated at OFC. And then my last slide looking at DCI and also subsea. It has been a little bit quiet this year if we look at Coherent records and Coherent technologies, but last year we did a collaboration with Fujitsu. They did 1.6 terabit at 256 gigabaud. So I think that was a very successful trial. We did that with Nokia, 1.6 terabit over 9,075 kilometer, single carrier transmission. And then also in the upper right, you see a trial with Nokia on, that was 1,200 kilometers with 2.4 terabit net single carrier bit rate. and that was also based on 300 gigabaud. So I think a lot of progress all across. If we look at chip-to-chip, chiplet connections, chip-to-chip, scale up, scale out, and then all the way to subsea. And when all those components seamlessly work and get deployed, then Ram's team comes into play, and the next 10 minutes, Ram will talk about how to make it all work in the system and optimize the system performance.
Wonderful. Thank you, Joachim. Hello, everyone. Nice to see you all. As Joachim said, I'm going to walk you through the next 10 or so minutes, really talking about what we see in the industry moving forward. And I'd like to kick it off by saying that we have a very unique vantage point in the industry. We see everything from early stage, silicon providers working on the next process node, all the way to the other end of the spectrum, to the hyperscalers deploying all this technology and offering all the services to the industry. So that broad perspective helps us to connect the dots. And what I'm going to share with you are 6 insights that we see coming in the near future. Some of it is already here. I'm actually very happy that I'm going after Deepak and Praveen today. A lot of what they spoke about is going to dovetail really nicely into some of the insights that I share here today. So the first is front-end scale now comes into focus, right? And you heard this extensively spoken about by Deepak as well. A lot of the focus before was on the back end and interconnecting the GPUs and getting all of the synchronization to work seamlessly and trying to work it as efficiently as possible, avoiding GPU idle time. But now, as agents are coming into play, more services are starting to get rolled out. Subscribers are starting to use AI. Enterprises, more importantly, are starting to deploy AI. The focus is also shifting to the front end, where a lot of that data needs to be accessed from public cloud storage, private cloud. You saw the petabytes of data that JP Morgan, or I think it was JP Morgan that had. So all of that data needs to be ingested and processed. And front-end, bandwidth, front-end optimizations, all of that is coming into play. And you're going to see a lot of new benchmarking that's going to happen between, storage networks that are maintained like in S3 or things like that and being pulled into, models that need to access them. So front-end is going to become a key focus area, first. Second, scale across, right? So we've all been familiar with the terms scale in within a chip, scale up within a rack, scale out across racks. Well, guess what? As we move up, now, it's no longer adequate. It's no longer, the industry is not able to fit the size of these 100,000 GPUs in a single location. And why? Because there's not enough power. So you have to now build the data centers where power is available. And what's happening is data centers are starting to get distributed into multiple geographic locations. And you need to provide some kind of DCI connectivity, interconnectivity between the data centers. And, I think Surendra and Venkat were brainstorming, and they figured out, called it scale across, and there's something coming as well. But the industry right now is generally looking at this type of connectivity so that you can scale and build larger models and offer, inferencing capability. So you might be curious, is there something beyond scale across? And people are talking about building data centers on other planets. People are talking about building data centers in all types of geographic locations where there is power. So we might end up, seeing something more than scale across being scaled beyond. But again, that's just a placeholder name. We'll see what the industry adopts and likes. But it's not going to be too far-fetched to think about, data center interconnectivity going through satellites in the near future. Heterogeneous designs are picking up steam. So you probably would have seen from Jensen's keynote at GTC this year, where he walked up on stage, there were 20 different racks from all the hyperscalers worldwide, all the vendors, different vendors. And, each one customized to that particular need and requirement that is needed. So I think we're very quickly moving away from a completely homogeneous, vertically integrated solution from a single vendor to something that is going to be now pervasive, which is everyone customizing these platforms with their own needs and working towards their own specific application use cases, right? And this variety is going to be good. You're going to get things like, I think Deepak spoke about Microsoft being on InfiniBand right now, but they're moving their scale-outs to Ethernet. Well, you're going to get a lot of Ethernet-based designs with this type of infrastructure, but it's not just Ethernet. People have been deploying with other technologies. You're looking at things like UA Link. You're looking at, obviously there's UEC. You're looking at SUE for scale-up. So this PCIe. So the industry is experimenting with a lot of different technologies in these racks to provide high speed, low latency, high bandwidth interconnectivity. I think at some point there are proprietary protocols that are coming into play as well that will need some kind of standardization so that you can have interop existing in the industry. So these systems are heavily customized for each vendor's individual requirements, and we will continue to see proliferation of these types of racks being deployed in data centers. Next, the fourth, domain-specific GPUs, right? So till now, we've had NVIDIA come out with their A100s and H100s and GB series of up to GB300s and so forth, and you have the Rubin coming out. But what's happening right now, as a lot of what Praveen also mentioned earlier in the day, is as these contexts are being built up, as tokens are being generated, you're ending up seeing, the current generation of GPUs are more general purpose, right? They kind of had a lot of GPU cores. They could crunch a lot of, math matrices. But now you're starting to see, more specialized GPUs that are specific to each industry vertical. Now, during that initial pre-fill phase, you want a lot of compute. You don't need that much. You don't worry about the latency and things like that. You need a lot of processing power. So now you're having specialized GPUs that are being built for that compute prefill stage. And when you're in the process of doing a lot of token generation, you're predicting the next token, your latency is very, very important. So now you have a family of GPUs that are really focused at inferencing and token generating. And on top of that, you have companies like AI making very, very specialized inferencing chips for video processing, for example. So you're going to start to see very specialized GPUs moving forward that are going to factor into all of this infrastructure that I'm talking about. So how do you now build a cohesive system that scales across many different applications? Well, that's what we get to next, which is composability, okay? This is going to offer the flexibility for different types of applications to, customize the infrastructure underneath that needs to support them. And, you have this, you cannot have like a fixed infrastructure with a fixed, amount of compute, fixed memory, fixed storage, fixed, CPU power and so forth. These applications are going to drive what, type of infrastructure needs to be supported underneath. So then think of it as you're going to have a pool of these different types of GPUs. You're going to have a pool of CPUs. You're going to have a pool of storage. And then the application developer is going to define, what they want that infrastructure. So it's going to be composable. And you're going to get to be able to choose a certain amount of X, Y, Z, bring it together, and then, have that infrastructure work in a heavily optimized way to support your needs. Last one is power-aware orchestration changes the grid AI dynamic. So you're all aware of how power-intensive AI has become. And the interesting thing here is, I think it was, if I'm not mistaken, I think it was Deepak that mentioned it. The slowest performing GPU or the slowest or weakest link in your AI infrastructure is going to govern, how good your overall, training time is or inferencing time is or whatever it is. And what happens is like this is, I think, a real example, I think maybe publicly that was disclosed by Meta. When they were performing a large AI training job, one of their GPUs overheated and automatically started running at half the rate or speed. And every other GPU that was involved in that as part of that training job then had to derate themselves as well, and it slowed down the whole thing, right? So you only go as quick as your slowest and weakest link. And what that did is, from a power standpoint, it just brought down and created these spikes, right? It brought down the power need for the overall data center to maybe half what it was consuming before. Now, the reason I bring this up is that moving forward, there's going to be some form of intelligent orchestration to facilitate how much power is being provided or is present. And then you're going to be able to leverage the infrastructure in the most optimal way to extract as much power as you need, and then get your job completion times optimized to finish within that power budget that's available. Okay? So in summary, there are 6 key things that we see right now from our vantage point. 1, front-end scale is going to come into focus. So you're going to look at it holistically from a system standpoint and really optimizing the overall system efficiency. Scale across is the new dimension. So we're not at scale beyond yet, but we're definitely going to look at data centers popping up in multiple geographic locations and how to interconnect them. Heterogeneous designs with a mix of all different types of protocols, interconnects, speeds and feeds. They're the reality and where the industry is moving towards. And we're happy to be participating in that ecosystem to enable that. Domain-specific GPUs are the future, and this is going to happen from NVIDIA. It's going to happen from a whole host of other companies that are building AI accelerator chips. Composability offers flexibility for applications. So, the applications are going to drive what type of underlying infrastructure is going to be needed. And lastly, you're going to see power-aware orchestration. So applications are going to become power-aware. They are going to have an orchestrator that knows where power is available, where infrastructure is available, marry everything together to get you the most optimal performance. So with all of this, I think the industry will eventually figure out AI, and we'll revisit Joachim's son now to see if, what does this robot do?
Hey, can you pour me some coffee?
Sure, Pablo. Here is your favorite coffee.
Nice.
Can you also make my bed, please?
I was not built to serve. I was built to outlast.
Dad!
AGI is going to be near. It's going to be near. Thank you, everyone.
Welcome back. We hope you found this session engaging and insightful, and stay tuned for more conversations about where AI infrastructure is headed next. Coming up on AI Unboxed, we have a fireside chat with the CTO of networking at Keysight. AI infrastructure represents a fundamental shift. It's the first time compute, networking, and storage must be designed, tested, and optimized as a single system. As AI continues to scale, that convergence is redefining what it really takes to build and validate AI systems at scale. In this conversation, you'll hear unique perspectives on how these pieces are coming together and what that means for the future of AI infrastructure. Michelle, I'll hand it over to you.
Hello, I'm here with Venkat Puella, CTO Networking for Data Centers here at Keysight. And we're going to cover some questions on AI systems. So let's get started. So good to have you here, Venkat. Thank you.
Thank you.
So tell us, how is AI different?
So AI is different because it's first time networking, compute, and storage are coming together. It's neither of them, but it's about how do you put all these 3 things together and optimize and debug set AI systems.
Mm-hmm. So tell us, how are compute, storage, network, how do they come together in this AI scenario?
So one of the things that is happening is that each of them come together one at a time, like network and compute come together and is forming in-network compute. That means you're doing compute in the network, which was like these were 2 separate things before. And storage and compute are coming together, which is forming computational storage. So interesting combinations coming up. So there's a tighter integration in forming an optimal system. It's not about individual components. It's about how all of them can work together. The other thing that is happening is how software and hardware are co-designed. So the software, how it relates to infrastructure, not as how software uses network. Instead, software using network and compute and storage together as AI infrastructure. So these are the changes.
And so with this new infrastructure comes new testing. So how is testing these AI systems different?
So, I mean, we're saying AI systems again and again, and that's the right thing, right? So somebody who is building this massive scale infrastructure like hyperscalers, earlier they used to test components, right? And we used to test individual components, make sure they're doing fine, and then whether they can kind of fit with each other. Now the issue, the challenge is that how does each of these components work in this massive scale? So that means you cannot test, you can continue to test individual components, but you have to test it as a system at a much larger scale. That is the key difference.
Tell us, is anything different for performance testing?
Yeah, so definitely. Earlier we used to do things like snake tests, which is kind of doing the same thing multiple times. Like if you take a router, packets are coming in, and we used to snake them through. The same packet is coming in 20 times or 30 times and then comes out. But in a way, if you look at it, it's only one packet coming in, one packet going out. We just repeat it 20 times. And that doesn't cut it for AI anymore, because the issues that are corner cases have increased with AI. And so basically you really have to test it at full performance. And then in terms of communication, what are the boundary conditions? In terms of storage, what are the new storage access patterns? So all of them need to come at the same time, and then you need to do performance testing. Otherwise, performance testing for the sake of performance versus performance testing under realistic conditions where all these different components are stressing in all directions. So that is changing.
So how do you test at scale?
The way you do at scale is to really test by building systems that are really high scale. But we can't build these high scale systems because they're costly. If you really want to test a 1,000 GPU system, it's going to be costly. The way we are trying to do it is by combining simulated components, emulated components, and combining real components. Real components because you really want to get a sense of what happens when there is a real congestion, when there is a real packets getting dropped, when real buffers are being shared, and things like that, right? At the same time, because you can't put so many of those components, we put high density emulation around it, right? High density emulation is again surrounded by simulation, which takes the scale to even higher level. So a simple answer, large scale systems would come by combining higher density simulation emulation with real components. And so that's how we are scaling the testing.
It's exciting, it's creative, and we appreciate your time. Thank you so much, Venkat.
Thank you very much.
That wraps up episode 1 of AI Unboxed. We hope you found today's discussion on how AI systems are evolving and what it takes to test them at scale, both insightful and actionable. There are some excellent questions in the chat. We may not get to all of them live today, but our experts will follow up with you by email. Thanks for joining us, and be sure to tune in next week for our next episode, where we'll dive into high-speed interconnects and software-defined networking.